Okay, so we're going to start with a review question. This was based on our last lecture, so we have 100 volt potential difference existing across a wire with a resistance of 400 ohm. What is the current flow? So we're looking for current. We know V and we know R. So we're going to do this guy. 100 volts. Looking for I. 400 ohms. And I, do the algebra real quick, is going to be 0.25 amps. So pretty straightforward application of Ohm's law. Now, what we're going to start talking about today is building circuits. Now, when you build a circuit, you're going to use this set of symbols here. So we're going to create what's known as a schematic drawing. So these here are potential sources. So these are basically your energy source. Every circuit has to have them. So you have a cell, which is a positive and a negative side. This longer side is the positive, and the smaller side is the negative. And we have a battery. We have batteries who are just a series of cells. So you can see positive, negative, but there'll always be one long side, which is always a positive side, and one short side, which is always a negative side. Now, these three will eventually come to play, but we're not going to worry about them today. This is a switch, which just allows us to open and close a different circuit, and then a voltmeter and an ammeter measure exactly that. They measure volts and they measure amps. We'll talk about later on how they get put into a circuit and why they get put in a circuit a certain way. And then we have these three things here. These three things here are all resistors. Now, this guy is a little complicated and we won't get to him today. This is a variable resistor. That just means that, well, quite honestly, that it can be varied. The way it's hooked up, because of the picture, usually is a little bit weird. We'll get there though. And this is a lamp. If you look at it, it looks kind of just like a little light bulb with a little squiggly in the middle, like the filament of the light bulb. That and that really are no different. Resistor is just a more general statement. A lamp is a specific resistor. Okay? Now, here we have the simplest of all circuits. So we have a voltage source. We have a full loop here. So it goes from the negative side to the positive side. And we have to have some sort of a resistance in there. So circuits must have some sort of a voltage source. It must have a full loop because all the electrons that are here have to go here all the way through the loop, drop all their energy along the way, and get here with no energy. And there has to be some sort of a resistor. If there is no resistor, then we short circuit. And that's bad. Nobody wants that. Okay, so this is what we have. Now, let's just do a quick example to show how Ohm's law comes into play with all this. So, just like we did in the beginning, let's assume we have 100 volt resistor, and we have, a 100 volt battery, and we have a 400 ohm resistor. Now, Ohm's law tells us this, V equals IR. So, that was the 100 volts we had before. We're looking for I, and this is 400 ohms. So I ended up, as we did before, to be 0.25 amps. Now, what does that mean? That means that the current that flows out of here, So the rate at which little charges are coming out of here is, remember, 0.25 coulombs per second. So we got basically a quarter of a coulomb per second coming out of here. Now, the bigger the resistance is, the slower this is going to be able to go. Because we think of this as kind of a one-way road, and this is kind of, let's say, speed bumps. Well, the more speed bumps you have, the slower traffic is going to be. With me? Okay. So, moving on. And here, we have basically as simple, but not quite as simple. This is what's known as a series circuit. Now, series circuit just means a circuit where there is only one path for the current. So, what do I mean by that? If we get over here, get a different color just to show it. The electrons come out here, right? They want to flow. They come here, they come here, they come here. They have to go over this guy, R2. They have to go over this guy, R1, and then here. So there's only one loop, one path. This is like a one-way street. So any current that comes out here has no choice but to continue to loop and to go here. That's going to come in handy later, okay? So for starters, let's talk about the current. Now, the current that comes out of the battery is going to be known as I total. Now, that just represents how many little electrons are coming out of the battery at any one time, or how many little charges are coming out of the battery at any one time. Now, based on the fact that this is thought to be like a one-way road, the amount of charges coming out of here at any one time can never be any more than the ones that are going through here, or the ones that are going through here. Now imagine if this is a one-way road, if there's 3 cars going by here every second, well, you can't have 4 cars going by here in a second, otherwise cars are going to have to be driving over other cars. So whatever the rate coming out of the battery is, the rate going through each of these objects has to be also. So the first rule we're going to come across is I total equals I1 equals I2 equals I3. Now this is hugely important because all this is telling us, or the major thing this is telling us, is if you know the current at one spot in a series circuit, you know it everywhere in a series circuit. So if I were to tell you that the current here was, let's say, 2 amps, you can immediately tell me that the current through here and the current through here was also 2 amps. Okay? Simple enough. Now, voltage or potential difference or potential drop, however you want to call it, that's a little bit trickier. So let's say this has a voltage of V. That means that the amount of energy each one of these little electrons comes out with is V per Q. So it's the amount of energy per unit charge coming out of here. Now, there are really only 2 barriers that the current runs into before it gets here. And if it came out with V, it has to have 0 V by the time it gets back to the other side of the battery, which means it has to lose all of its voltage over just these 2 items. So the voltage dropped over the first one, or the way, we'll go backwards. The voltage dropped across both of these guys, V1, and V2 has to add up to whatever came out of it in the first place. Think of it as money. Let's say you leave your house with $100. You go to 2 stores. You spend all of your money. And let's say I told you I spent $60 here. That means I must have spent $40 here. Right? Because the amount of money spent at each one of those places, the amount of energy lost at each one of these places, has to add up to the original amount. Okay. So we have a rule for V. We have a rule for I. Now I want to come up with a rule for R. Rule for R is not terribly difficult, but we do have to do a little bit of algebra. So we got V total equals V1 plus V2 plus V3 plus dot, dot, dot. Okay. Now, we don't want a rule for V, obviously. We want a rule for R. So we have V equals IR. Now, that means I can replace each one of these with the appropriate, replace each one of those with the appropriate IR. So this would be I total, R total. This would be I1, R1, I2, R2, and so on and so forth. Now, almost there, because now we have an R in every single one of our terms. But we want a rule for just R, not for I and R. But we could take advantage of this guy. Because if I divide this by I total, algebra tells me I have to divide everything by I total. And what we hopefully realize now is that I total and I total would go away, and you just have R total. I1 and I total are equal to each other, so those would also go away. I2 and I total equal, equal, so on and so forth. What you eventually end up with is R total equals R1 plus R2 plus R3 plus dot, dot, dot. Okay, now, before you start to panic, two things I want to point out that are going to make you feel better. One, this need to know never going to be asked in the Regents exam. So while it's nice to know where this came from, you'll never, ever, 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 ever need to know that. Number two, it's already on your reference table. So you're not going to have to memorize these formulas. On your reference table, it says it a little bit differently. So if you look here, I wrote I total, it just writes I. So if you want to write on your own reference table even I total, fine. If you want to write V total, fine. Now, what they did here, and I'll explain later, it makes a little bit more sense when we do parallel circuits, but for series circuits it also works. This EQ stands for equivalent. What that basically means is you can take out all those resistors set up the way they're set up and put in one resistance that would be the sum of all of them, and it would be equivalent to all those other ones. But long story short, you have these rules. Makes life a little bit easier. Okay, so let's go back and actually do an example. So I'm going to say that this guy is 100 volts. And I'm going to say this guy here, I'm going to get rid of those. I'm going to say R1 is 10 ohms. I'm going to say R2 is also 10 ohms for now. So, first thing I want to do is I want to talk about these three values. So V total, pretty obvious. V total is, silly. V total is 100 volts. It's the total voltage that the circuit has. Now R total, we just said the rule for R total. So it's going to be R1 plus R2 in this case. So R total is going to be 10 ohms plus 10 ohms. So R total is 20 ohms. Now I total. Well, for I total, we're going to take advantage of Ohm's law using our subscripts. So V total we just said was 100 volts. We're looking for I total. And R total we just found to be 20 ohms. So a little bit of algebra. We would find that that's 5 amps. to find out V1 and I1. Oh. Being just the voltage drop across R1 and the current through R1. Well, this one is nice and easy. Current through 1 is just that same 5 amps. Because remember, our rule is if I know the current here, which we just found to be 5 amps, it's got to be 5 amps here and 5 amps here. Now, in order to find V, in order to find V there, we have to use Ohm's law again. V1, I1, R1. So we're looking for the voltage drop just across 1, which is going to be 5 amps times 10 ohms, or be 50 volts. Now, V2 and I2, well, these are even simpler now. This is obviously 5 amps. Since that's the same resistance as this one, this also has to be 50 volts. Now, another way we could have thought of that is if this was 50 volts, that meant that we lost 50 volts over this object. If I had 100 to start with and I lost 50 here, and there's only one other object, I must have also lost 50 there. Make sense? All right. Let's try one more. Use the same diagram. I'm just going to change things around ever so slightly. So, let's change up the pen a little bit. Be fancy. Let's call this 200 volts. I'm going to call that 5 ohms. And call that 15 ohms. So now, this will be R1, this will be R2. Now, these are different resistances, so it's not going to be exactly the same. So let's take our totals. Oh, let's do our total values first. So we got V total, we got R total, I total. So V total is obviously 200 volts. R total is just going to be, again, the straight sum. So that's going to be 20 ohms. And I total, if you did V equals IR, that's just going to be 200 volts. Looking for I total. And R total is going to be 20 ohms. So I total should be 10 amps. Now we got V1 and R1. We know R1, that's silly. V1 and I1. And V2 and I2. Again, knowing our current has to be the same everywhere, and we've already found the current coming out of the battery, then we know that this again has to be 10 amps. Now, V1 is going to be V1 equals I1, R1. So V1 equals 10 amps times 5 ohms. V1 is going to be 50 volts. Now, as I said before, you can very easily do V equals IR again for this guy. Oh, let's undo that. Nope. So this is 15 ohms. So you could very easily just do V equals IR for that guy, or we could take advantage of the rule that V total is equal to V1 plus V2. And if V total is the 200 volts, and we just found V1 to be 50 volts. Well, V2 just has to be whatever's left over from the 200. So this guy has to be 150 volts. Okay, so that is basically it. So What you really need to know is that Ohm's law is your friend. You have to know your rules for series circuits. And, well, you really just need to know to take your time. Think it through. It is not necessarily the easiest thing in the world to do. So, if you take your time, you'll eventually figure it out. All right? Well, hopefully this lesson wasn't too terribly difficult for you. You have those questions that I posted on Castle Learning. It's going to be the second of the assignments I assigned for you, and it's all on these series circuits. All right? So hopefully those go well, and I will talk to you guys all on Friday. All right?